All right, first we'll talk about some of the problems that were on the first set of PowerPoints that I went over. Um, One of the problems that you were asked is for the reaction of CH3 manganese CO5 plus PPH3 to show the steps of that reaction. Um, I was happy with either answer for this. So you could show sort of the 3D structure, or you could start just with formulas. Either one of those would be fine. So if you wanted to show it just with formulas, what would happen is this CH3 would end up attacking one of the COs, and so you'd get CH3C double bond O manganese CO4. That would be your intermediate. This is what initiates the reaction. And if you went in and did your electron counts here, this first structure here, this is an 18 electron complex. This becomes a 16 electron complex. And it does that because I took a 2 electron ligand and a 2 electron ligand, and finally that became one 2 electron ligand. So 2 plus 2 gave me 2 uh, for the total electron count here. So I lost 2 electrons being donated to the metal complex. So this is a 16 electron complex. And then from that point, PPH3 can come in and coordinate to the metal. Okay, if I wanted to be a little bit fancier with that, I would put my structures here. Okay, and then I can show a little bit more detail when I have this 3D structure. So it's going to attack one of the COs that's next to it, and it doesn't matter, they're all equivalent. Okay, and just like before, this started out as an 18 electron complex. This went down to a 16 electron complex. And then the phosphine comes in, plus PPH3. To bring everything full circle back and have an 18 electron complex. So a similar question I also ask you at the end of that video to go through and do the electron counts for this catalytic cycle for catalytic hydrogenation by Wilkinson's catalyst. All right, I'll start here with the starting complex. So chloride is chloride minus. That means rhodium must be plus because the phosphines are neutral. So rhodium plus 1 is a D8 metal. 3 triphenylphosphines give me 6 electrons, and a chloride gives me 2. So this is a 16 electron complex. So standard 16 electron complex, square planar. This is from actual experimental work, they found that for this reaction to happen, you need to lose one of the phosphines. But that's the only thing that's changed here. So you still got your chloride, it's still rhodium 1. And so what has happened here is I have rhodium 1. I only have 2 triphenylphosphines for 4 electrons, and I have a chloride still for 2 electrons. So this is just a 14 electron complex right now. So this is very reactive. It reacts with H2. And now let's figure out what's happened to our metal center. So chloride still minus. Hydrogen, when it's connected directly to a metal, is a -1 ligand also. So those are hydrides. And the whole thing here is neutral. And so this is now rhodium 3 that we have. So rhodium 3 plus. Okay, rhodium 1 was D8, so this is a D6. I have 2 triphenylphosphanes, 4 electrons. I have 1 chloride, 2 electrons, and I have 2 hydrides for 4 electrons. So that is 16 electrons right now. 16 electrons. All right, and then what happens is this is an alkene that comes in. The alkene binds and acts as a 2-electron donor. And so, lost a ligand here. Lost my chloride. Chloride minus, chloride minus, chloride minus. This alkene is neutral. So I have rhodium 3 plus still, which is still D6. I have 2 triphenylphosphanes, which contribute 4 electrons. I have a chloride, brings 2. I have 2 hydrides, which bring 4. And I have a 1 alkene. And that double bond there acts as a 2-electron donor. So this brings us up to an 18-electron complex. All right, well, what's happened here? So now it's going to get more complicated. We have a chloride. Okay, so we have chloride here, which is a -1 ligand. We have hydride here. This is -1 ligand. One of the hydrides reacted with the alkene to give this alkyl group. An alkyl group is also a -1 donor. So I haven't done any redox here. It's still rhodium 3, still D6, 2 phosphanes, 4 electrons, 1 chloride, 2 electrons, 1 alkyl group, 2 electrons, 1 hydride, 2 electrons, so 16 electrons. So this is similar to what we saw on the previous slide. So the hydride and the alkene, so the hydride's a 2-electron donor, the alkene's a 2-electron donor. Once we do this insertion, we get 1 2-electron donor out of that deal. So this 18-electron complex became a 16-electron complex. And then finally, what happens is this hydride and this alkyl leave as an alkane, and in doing so, the metal gets reduced from rhodium 3 back to rhodium 1. And then you can react with H2 again, react with an alkene again, and go around the cycle over and over. Okay, so now I'll walk you guys through the solution to the alkene isomerization question that I asked on the second day. And here's the 3 different alkenes that we talk about in this problem. 1 butane, so it has a double bond between the first and second carbon, and 2 butane, which has a double bond between the second and third carbon. This one can be called a terminal alkene because it has the double bond at the end, and these 2 down here at the bottom are internal alkenes because the double bond is not at the end of the molecule. So what you'll want to do to understand this is sketch it out with wedges and dashes the way that I have. And so for clarity, I've not put all the CO ligands in. So the first thing that you need to do is lose one of your CO ligands and then bind the alkene. That's the first step to get to this intermediate, and then you go from there. But let's look at how I've drawn this structure. So I have my cobalt, I have a hydride, I have the alkene cis to it. It's 90 degrees away, the 2 ligands in this complex. And this is cis-2-butane, and I've drawn both of the methyl groups away from the viewer and both of the hydrogens on the alkene toward the viewer. And throughout here, I've made this hydrogen that starts out here on the metal be purple. So cobalt with a hydride. This hydride comes over and it attacks at the red carbon. And when it attacks at the red carbon, the cobalt forms now a single bond to the green carbon here. So that's the first step that I show right here. So now a hydride and an alkene became just an alkyl ligand. If this, and this does, if this just went straight back, it would be a very boring reaction. So part of the time it's just going to go straight back, and this hydride gets dropped back onto the cobalt, and then there's nothing productive that happens. But let's talk about the things that can happen from this to give us isomerization. Probably the easiest one to talk about is cis-2-butene to trans-2-butene, because that now, once we have this is a carbon-carbon single bond that's here, and we have free rotation around a carbon-carbon single bond. So that rotation happens. This purple hydrogen rotates around to the back, and this other hydrogen here rotates toward the metal, the one that's black. It goes and it does, this is a beta hydride elimination. It goes and it takes this hydride, it puts it onto the metal center, and now what we've got is a cobalt hydride with now a trans-2-butene. So we have one methyl group pointing back and one methyl group pointing forward. So it's trans where it started out cis at the beginning. So now in the solution, if this dissociates into the solution, you've done an isomerization from cis-2-butene to trans-2-butene. Well, we have another pathway that happens in that same solution. So if I go back to this intermediate, there's another type of rotation that we can do. You can also do a rotation around a cobalt carbon single bond. And so that's what happens from here to here. We do a rotation about this bond, and the methyl group that started out back here now becomes this methyl group where I've drawn out all the CHs. So the one that was back here becomes this one. We rotate the whole thing around. And then now if any one of these drop onto the metal through a beta hydride elimination, what we're left with is a 1-butane. Now we have the double bond on the end of the molecule. So these are the ways that we could start out with cis-butane and end up at the end of the day with a mixture of cis-butane, trans-2-butane, and 1-butane from that mixture. Just through ligand loss, alkene coordination, we have alkene insertion reaction, rotation, and beta hydride elimination. Okay, next we'll go over these day 3 questions that were in the slides for day 3. And we're going to look at possible quantum numbers. So I give you sets of quantum numbers, ask you if it's allowed or forbidden. If it's allowed, I ask you to then go ahead and name it. For this, and usually people would have to memorize this, but obviously you guys will have access to whatever you want to use during the exam. I'll write the rules that we have here. So n can have values from 1 all the way to infinity. Okay, integer values from 1 to infinity. L has values from 0 all the way up to n minus 1, determined by whatever the current n value is. M sub L has values from minus L through 0 to plus L. And then M sub S has values of plus 1/2 or minus 1/2. So I always suggest you just go left to right in each one of these rows. So n equals 2 is okay. L equals 0 is okay. 2 minus 1 is 1, so that's okay. M sub L equals 0 is okay. And M sub S equals plus 1/2 is okay. So this is allowed. The first part of the name is just whatever the n value is, and the second part comes from the L value. So we have S, P, D, F, 0, 1, 2, 3. So L equals 1 gives me a 2p orbital. All right, let's look at this next one. So n equals 3, that's okay. L equals 2 is okay. M sub L equals minus 1, okay. And M sub S equals plus 1/2, okay. So that one's also okay. It's a 3d orbital. All right, now looks like we're going to run into some trouble here soon. So that's okay, that's okay. So based on n, the L value is okay. Now I need to say whether based on L, the M sub L value is okay. So based on this L value, I expect M sub L values of -1, 0, and +1. So not okay, and that's okay, but any break in here means that the quantum numbers are forbidden. So they all have to be allowed. So it's forbidden, so I'm not going to name it. Okay, so based on this N, this L is okay. Based on this L, this M sub L is okay. But then I have this strange M sub S here. And it can only be -1/2 and +1/2, so that doesn't work. All right, N equals 4 is okay. If N is equal to 4, L will go 0, 1, 2, and 3 because it goes up to N minus 1. So this part's not okay, so that one is a no. All right, next. How many d orbitals are possible for N equals 6? N equals 6. L will have values from 0, 1, 2, 3, 4, and 5. But for a d orbital, the L value is 2, so that's all that really matters here, is that the 2 is allowed. And then if L equal 2, M sub L equals -2, -1, 0, +1, +2. So there would be 5 values allowed. All right, then how many f orbitals are possible for n equal 3? If n equals 3, then L equals 0, 1, and 2. So if L is equal to 2, that's a d orbital, so this was a trick question. There's 0. Okay, there's no 3f orbitals. All right, we'll look a little bit at the day 4 question. I had given you all the equation for a 2-electron atom or ion. So it's this alpha squared minus 2 times z times alpha plus 5/8 times alpha. The z is the atomic number, and so specifically the question was about lithium, so the atomic number is equal to 3. So there's a few different ways. So you're asked for what's the optimal alpha, and that's the one that will give you the most negative value of the energy. So there's a few different ways to approach it. So if you want to know what value of alpha gives you the absolute minimum, you can try some and try to narrow down where that would occur. So for example, I'll do alpha equals 1 here. So that's 1 squared plus, or excuse me, 1 squared minus 6 times 1 plus 5/8 times 1. That gives me my E2 is a minus 4.375. Hop over to 2, because right now we don't know if the energy is going to go up or down when I go to 2. So 2 squared minus 6 times 2 plus 5/8 times 2. So alpha equals 2 minus 6750. 3 squared minus 6 times 3 plus 5/8 times 3. Oh, I messed something up there, I think. Oh, yeah. 3 squared. There we go. Alpha 3 E2 minus 7.125. Alpha 4 squared 6 times 4 plus 4 squared 6 times 4 plus 5/8 times 4 minus 5.5. Okay, so we know that the minimum of the value, the minimum value, the alpha that gives us the minimum value of the energy, then is somewhere in here or in here. It's somewhere between those two. So let's try 2.5. 2.5 squared plus minus 6 times 2.5 plus 5/8 times 2.5. Okay, this gives me minus 7.1875 for alpha equal 2.5. Okay, so that's lower than any of the values that I have. So then we could go and just try in between here and between here, and we could get this to however many sig figs we wanted it to be, to know that we were at the absolute minimum. We could go, 2.75, and then 2.6, and down and down and down and down. Okay, probably the easier way, both to visualize this as well as to talk about it, is to just graph it, and I've done this, and you can do this with a free calculator. This Desmos calculator will do this for you. So y equals x squared minus 2 times 3 times x plus 5/8 x, and you'll see basically what we were doing here. So there's the value of 1, there's the value at, there's the value at 1, here's the value at 2, here's the value at 3, and yeah, 2.688 was the minimum of this. Okay, and then from the graph, you can get the number here directly, or you can put it into your calculator to solve for it, and you would figure out within this model what is the minimum energy of the lithium plus cation. All right, on day 5, I ask you to write out the energy of 2 different excited states of the helium atom. This one's called the singlet state, where we have 1 electron up, 1 electron down, so that overall there's no total spin. This is plus a half, this is minus a half, so you add those together, you get S equals 0. Here, the triplet state, we have both of them up, so it's plus a half, so we have total S equal to plus 1 here. So this is called the singlet state, this is called the triplet state. So the first few terms of this will be boring. So this electron here in the bottom on both of them will have an H11. Okay, that's the, we'll have a T11, that's the kinetic energy of electron in a 1s orbital, T11. And it will also have a V11, both of them will have a V11. That's the attraction between the electron in that orbital and the nucleus. What else is boring is the 2s. So the 2s will have kinetic energy, and it'll have potential energy. It will have kinetic energy, and it will have potential energy. All right, something else. There is an electron in a 1s and a 2s, so they'll have this J12. J12. That's the repulsion between the 1s electron and the 2s electron. That's going to be the same. And however, for the triplet, there's going to be one additional term. So this is an up electron, and that's an up electron. So we'll get a K12. And that is an exchange interaction because they're both up. And so when I do my total energy here, okay, it's plus, so this plus this plus this plus this plus this minus that. This plus this plus this plus this plus that. And so T11, V11, T22, V22, all the same. J12, J12, the same. The difference here being this minus K12. So the triplet is more stable. Okay, it's going to have a more negative energy because of that additional K12 term. In the day 7 video, I asked that you draw BF3 and benzene and show me some of the symmetry elements that was in there. I'm going to use the Otterbein site to show it to you guys, the symmetry elements that are in those molecules. So the first one for BF3 here is a C3 axis. I can do 1/3 of a full rotation to interconvert the fluorines in the molecule. So there is the C3. This molecule also has 3 C2 axes. The C2 axis goes through a boron and one of the fluorines. And if I turn them all on, there's one that goes through each BF bond. The molecule itself is flat, so it has a mirror plane that is the plane of the entire molecule. And then some other mirror planes that it has. It has a mirror plane that goes through each BF bond. So there's just one of those. It will reflect this fluorine into that fluorine and this half of this fluorine into that half of it, of that same fluorine. Lots of symmetry elements for benzene. So benzene, its highest rotation axis goes right through the center, doesn't touch any of the atoms. There are lots of C2 axes. There's a C2 axis that goes along the same axis as the C6. There's also these C2 axes that go through atoms. And it's interesting to compare those to, so the ones that go through atoms to the ones that go through bonds. So they're two different types of C2 axes that we have here. There's an inversion center. That's a point in the very center of the molecule. Remember, inversion takes everything and brings it into the middle and explodes it back out again. It's planar, so there is a mirror plane that contains the molecule, and then there's all these different mirror planes that, again, some of them split the bonds, and some of them go in and split the atoms. In the Day 8 assignment, I ask you to look at 1,2-dichlorobenzene, 1,3-dichlorobenzene, and 1,4-dichlorobenzene. And again, I'll use Otterbein here to show you guys some of the symmetry elements and help you figure out the point group. So for 1,2-dichlorobenzene, the highest rotational axis that it has is the C2 axis that goes through both the bonds here. It doesn't have a horizontal mirror plane. Recall that horizontal would mean that it needs to go this way. So the primary axis is up and down, so right and left, there's not a mirror plane here. So it is not an H-type group at all. But it does have two mirror planes that contain the primary axis. One, which is the plane of the molecule, it's the easiest one to see, and one that's perpendicular to that. So this is the C2V point group. Here we have 1,3-dichlorobenzene. It actually ends up being the same point group. We have our primary axis that goes straight up and down here. There's no horizontal mirror plane. There's two vertical mirror planes, so this one is also C2V. Finally, here we have the most symmetric of the group. We have the 1,4-dichlorobenzene. The highest axis that it has is a C2 axis that goes right through the middle. This one does, however, have two perpendicular C2 axes. So this belongs to some sort of a D group. So it's a D2 of some sort. And after this, we need to see, is there a mirror plane that is perpendicular to the primary axis? The primary axis is the Z-axis, the one that goes through the middle here. There is, and so this is D2H point group. So, and finally on day 9, I ask you to provide one example each of the following point groups: C2H, C2V, D2D, and D2H. A real fun way to think about this is to go and look at this symmetry gallery and think about what changes you could make to a molecule that you were given that would keep it in the same point group, but would give you a different molecule. So for example, for C2V, real lazy example here might be so we've got H2O. If I change out the oxygen to a sulfur, that's also C2V symmetry. And that's because I made the change here on the primary axis. Okay, if I made the change instead out here, I would either have to change both the groups. So for example, I would have to make both of these be fluorine, so OF2, because if I change just one, then I would lose my reflection that's here, and I would lose my rotation that's there. Here's another one that you could think about. So for example, this one is C2V that we talked about earlier. So we could make any changes that respect the symmetry that it has. And so, for example, I could take, so these are bromines, I could make this be, say, 2 chlorines that are up here. Whatever change I would make would need to respect all the symmetry elements that this molecule has. And so if I made these chlorines or fluorines, I would need to make both of them so that I could still have that mirror plane that was there. So that's probably the easiest way to think about those sorts of things, is to go in and look at a molecule that has that symmetry, and then think about what changes you could do to that molecule. So for example, you would think about what changes could I make to this molecule that would respect all of these symmetry operations. Well, this one would be pretty tough, actually. So if I took it, because it has this inversion center, and the inversion center says that any point that I go to, there has to be a corresponding opposite point. So if I go right and up to this hydrogen, I have to go left and down to that hydrogen. I would have to substitute this one and this one if I wanted to do, say, hydrogen to fluorine. Well, now I've killed this mirror plane. So really all I could do for this one would be to go in and say replace all of them by fluorine, and that would keep the same point group for that molecule. So it's a fun and interesting way to approach these, is to go in and see what changes you could make to keep the point group that you have an example of, without what changes can you make without destroying that point group symmetry.